when electrons are circling atoms, it's creating an electromagnetic force field, just like a lightsaber. This guy will blow your face off before he loses that electron, and this guy will tear your lungs apart and fill them with acid before he picks up that electron. Chemistry is crazy. Redeem Academy. Yo, what is up, science squirrels? Johnny here with Redeem Academy. I'm here to help you get the most out of your education while giving God the glory he deserves. We are in lesson 4 of our chemistry unit that is in the middle of a whole year of biology. And I'm going to be teaching you 3 things today. I'm going to teach you the basics of bonding. I'm going to teach you about 2 types of bonds. And I'm going to teach you a little more about salt. The big question today, how could chemical bonds be used as a metaphor to compare God's design of marriage with the human invention of dating? All right, now I want to give a shout out to our sponsor today, salt. That's a beautiful little chunk of salt, isn't it? Wish there were a calm, dependable way to season your popcorn without a fireball that burns off your eyebrows? Try salt, now with 0 explosions and 100% taste. And while you're at it, subscribe to Redeem Academy and grab your notebook at redeemacademy.org. All right, today's on bonding. Let's get into the notes. All right, big idea today is a bond that is a connection between 2 atoms. In the last lesson, we talked about the fact that atoms' behavior is largely driven by their desire to fill their outer shell with 8 electrons. And now that's different for the first 2 atoms, helium and hydrogen. They only need 2 outer electrons. But then everybody else, they want a full octet. They want 8 electrons in their outer shell. And so this strong desire that atoms have to fill up their shell with electrons, and 8 is the magic number, that is what drives atoms to form bonds. So this statement here, this is what an atom really needs to be happy. They want a full shell. And you're going to see this over and over again today, that the thing that is going to cause the 2 different types of bonds to occur is atoms seeking a full shell. So basically, my lesson today, I mean the title is bonding, but my lesson today is basically going to be about 2 types of bonds. This type of bond is called a covalent bond, and this type of bond is called an ionic bond. We're going to start with the ionic bond. All right, so we're going to watch this video, and the question that we're going to answer with this is, how do ionic bonds work?
How do atoms join together or bond to form molecules? Let's take a close look, really close. Atoms aren't even big enough to be microscopic. As teensy as atoms are, they're made up of even smaller particles, neutrons, protons, and electrons. A diagram of an atom looks like this. Shells surrounding a center or nucleus. Inside the nucleus are all of that atom's protons and neutrons. Moving all around the shells are that atom's electrons.
All right, so did you catch that? In this diagram, the yellow particles are the electrons. The red particles are the protons, which is exactly backwards of what I did. I did red was electrons, not protons. And then they have these tiny little black ones right here that represent their neutrons, which is fine because we don't really need to pay attention to the neutrons.
Inside the nucleus are all of that atom's protons and neutrons. Moving all around the shells are that atom's electrons. Let's focus on protons first. The protons in the atom's nucleus stay there. An atom of a particular element will always have and keep the same number of protons. That number of protons is so permanent, memory trick here, proton and permanent both start with P, that it's part of the information in the periodic table. That number, usually at the top of each square, is the atomic number, the number of protons in the nucleus of an atom of this element. Look at sodium.
I like this video. It's a really good review for everything you've learned so far.
Abbreviated Na. A sodium atom has 11 protons in its nucleus. The atomic number also tells you how many electrons there are. Individual atoms of every element have the same number of protons and electrons. So a sodium atom has 11 protons, 11 electrons. All right, pop quiz number 1. How many electrons are there in an atom of chlorine?
Okay, think about it for a second. How many electrons in an atom of chlorine? Say it out loud, right now. Do it.
Answer, 17, same as the number of protons.
If you didn't get that one right, it's okay. I want you to raise your hand. I didn't get it right. Mr. Olgers, put your hand over here. Slap yourself in the face. There's another question. Get ready.
The number of protons and electrons in each atom is the same. Protons and electrons are very different, with different electric charges.
Okay, here you go. Quiz time. You're going to get this one right. Protons and electrons have different electric charges. What are those charges? Here come the answers.
Protons have a positive electric charge. Add to the earlier memory trick P for proton, permanent, and positive and plus. Electrons, which by the way are much smaller than protons, are the opposite. They have a negative charge. And atoms themselves? All right, heads up, this next part contains information that might prove useful in a later quiz. Because atoms have equal numbers of positive protons and negative electrons, the electric charges cancel each other out. So the net charge, 0.
0. Remember learning about that when we learned about ions?
Okay, now back to electrons. While the positive protons are permanently in the atom's nucleus, the negative electrons in an atom are not. Electrons move around in the shells. And this is key, unlike protons, the number of electrons in an atom can change, and do when and if atoms bond.
Oh.
To explain this step by step, let's use a simple everyday example. How atoms of the element Na, sodium, and atoms of Cl, chlorine, form a bond, an ionic bond, to make NaCl,
ionic bond.
the abbreviation for sodium chloride, more commonly known as salt. Now, atoms bond by...
Okay, now we're going to pause the video because I want to tell you all about chlorine today. So you already know about sodium, but you don't know about the terrible story of chlorine. Here we go. All right, so I just was online looking for videos of chlorine gas, thinking I'd find something about World War I, and I did, but I also found this video. Now, this happened 3 years ago. It happened in Jordan in 2022. Jordan is a country right next to Israel. So you see this tank right here, and it's suspended in air by a crane right here. Now you can't really see what's holding it up, but in a second what's holding it up snaps and it drops and it breaks. So just look at what happens when all this chlorine gas breaks out of this tank. It's probably a liquid under pressure, and then once the tank opens, all that liquid gas evaporates out, and you get to see what chlorine gas looks like. Okay, and you can see like all these people running. They're running for their lives. Okay, even the guy driving the truck is driving away. That might be another tank of chlorine gas right there. You can go forward. 12 people died. Probably the people inside the ship probably died. So there's a view of the crate. You can see it got pierced by something when it fell and broke open in 2 spots. Now we're lucky to live in a time in human history where we don't poison each other with this stuff anymore. But in World War I, they were trying this stuff out. War is terrible, and humans have done some of the most awful things to each other, and so this is an example of that.
First World War technology, chlorine gas. In 1914, a chemist called Fritz Haber offered his knowledge to the German army. He soon began experimenting with chlorine gas to be used in trench warfare. In April of 1915, 150 tons of lethal chlorine gas was used by the German forces against the French army at Ypres. The French soldiers witnessed yellow lime clouds with a distinctive smell of pineapple and pepper slowly drifting toward their trenches. The French infantry assumed that the Germans were merely using a smokescreen at first, until they started to complain about pains in their chest and a burning sensation in their throats. As the realization of a gas attack became apparent, the French ran away from the area, putting a gap in the Allied line. The German army was hesitant to advance forward due to concerns with what the chlorine gas would do to them. This enabled Canadian and British troops to recapture the position before German forces could break through.
Now this was just the beginning of the use of gases in World War I because people were in trench warfare. And there were other gases. There's a second gas, which you would think chlorine gas would be called mustard gas, but there's a second gas like it called mustard gas. And people started poisoning each other with different gases, and this was really the beginning of chemical warfare in World War I. Now what chlorine gas does is chlorine, they actually use chlorine to kill things in pools, and it bubbles up through the water and it connects with the water to make hydrochloric acid. And so if you breathe in chlorine gas, you get acid in your lungs, and then that will scar up your lungs and destroy tissue. It connects with moisture that's in your lungs. Lungs are very moist on the inside. And then that causes more moisture to come in and more mucus. And so the lungs will begin to fill with fluids, and you'll kind of like not be able to breathe anymore because you're trying to breathe still, but it's not working anymore. And so those people who died in the trenches probably died of asphyxia, which basically means you're trying to breathe, but you're not getting enough oxygen in and out. And so you just die because you can't breathe. But it probably took 15, 20 minutes for them to die, maybe a couple hours, depending on how badly they scarred their lungs with acid. Or you survive and your lungs are really compromised, and you're probably going to get killed at a much younger age from an infection like influenza. So just terrible, terrible thing. Now, another scary thing, just be careful. Don't ever mix cleaning chemicals that you're not sure what you're doing. So 2 really good cleaning chemicals, bleach and ammonia, if you mix those together, that will actually produce chlorine gas.
Don't do it, okay?
Just don't ever do that. You could potentially kill yourself in the bathroom trying to clean the sink or trying to clean the toilet or something.
Okay?
Not a lot of people have ammonia that they're using to clean things. Like concentrated ammonia is not really a common chemical around the house anymore. So anyway, we've got this metal that likes to explode in water, and then we've got this gas that is so deadly, it'll kill you if you breathe it in. And those 2 things come together to make salt. Here we go.
Look how many electrons chlorine has in its outer shell. 7. Sodium, 1. So sodium gives up 1 electron, which chlorine picks up. That gives chlorine the magic 8 electrons in its valence shell. Giving up that 1 lone electron empties sodium's outermost shell. Think of it as a go fish player with no cards to trade who has to drop out. The second shell now becomes the outermost valence shell. It still has electrons to trade, actually 8 of them. So sodium too now has its magic 8. Pop quiz number 2. Now how many electrons are in each sodium atom? To remind you, this is sodium.
Okay, so I mean, this is a lot of information, especially with my big distraction in the middle there, but if sodium loses an electron, it loses a negative thing, and the question says, now how many electrons are in each sodium atom?
Sodium's atomic number. Answer, 10.
10.
It gave 1 of its 11 electrons to chlorine.
All right, so sodium lost 1 of its electrons, so now it only has 10 electrons.
The positive protons in the atom now outnumber the negative electrons, 11 to 10. So sodium is no longer neutral.
All right, we need to stop and write some of this down. Okay, so I'm going to draw sodium a little different than they draw it in their video. I'm not even going to draw the protons. I'm going to draw sodium's name, Na, and then I'm going to draw it in blue. Blue represents positive. And I'm going to draw how many protons sodium has in its nucleus. So I'm going to write plus 11 right here. So I got sodium plus 11, okay? And then I'm going to draw all of sodium's electrons. So I'm going to draw each one as a circle. Okay, now that's 10 electrons, but sodium has 11 electrons. So there is 1 more electron in another shell out there, but I haven't drawn that shell because this electron doesn't want to stick around. Now let's look back at chlorine.
Sodium, 1.
So remember, sodium's here with this 1 extra electron, and it wants to donate that electron to chlorine.
So sodium is no longer neutral. It now has a positive charge, indicated with a plus sign, and is a sodium ion. That's the term for an atom with an unequal number of protons and electrons.
Do you remember that? Okay, that's lesson 3, ions. When an atom has a charge, it's called an ion.
Pop quiz number 3. How many electrons are in chlorine now?
Okay, so chlorine just picked up something from sodium. How many electrons does chlorine have if its atomic number is 17?
Answer, 18, which means the chlorine atom is now an ion too. 18 negative electrons outnumber 17 positive protons.
All right, now let's go back to the notes. So here I'm going to draw chlorine. Now chlorine is number 18 on the periodic table, so it gets plus 18, representing its 18 protons in its nucleus. And I am now going to draw all of its electrons. Oh boy, I make the dumbest mistakes. Chlorine is number 17 on the periodic table. I'm going to fix that. Sorry about that. All of you at home, I'm sure, have some whiteout. Not. Ugh, can you even tell that says 17? My bad. I'm going to draw a little arrow. My bad, guys. Plus 17 is what that says. Okay, so I apologize for that giant mistake, but 17 protons and then 17 electrons, and now this electron is going to come and land in this empty spot. That makes sodium have a full shell, that makes chlorine have a full shell, and now I'm going to draw an arrow down to here, and all I'm going to draw is a bracket, because I'm going to draw sodium as an ion. Because sodium has 11 protons and 10 electrons, I am going to draw sodium as blue because it has a positive charge. I'm going to write Na, and I'm going to put a little plus here because it's got a positive charge. Okay, and then right next to it, I am going to draw chlorine, and I'm going to use red for chlorine, and I'm going to write Cl, and on the outside I'm going to put a little minus, and positive things like to connect with negative things. Just like boys are attracted to girls, and girls are attracted to boys, positives are connected to negatives. And I'll let you decide who's the negative and who the positive is. Here we go, let's let our video finish this idea off.
Gives chlorine a negative charge and changes its abbreviation to Cl-, also changes chlorine to chloride. You probably know opposites attract. Positive sodium and negative chloride ions are strongly attracted to each other. And that attraction is what bonds Na+ and Cl- ions together to form NaCl, sodium chloride. Most chemical bonds are ionic, like the ones that form salt.
All right, now, there's a mad scientist in the world who makes fresh salt for his popcorn, and I must show you this. Check this out. You see that fish net full of popcorn? This homeboy in the white hat is like a mad scientist, and he's got this cool lab that this other guy showed up to see how he does this. And he's going to make some fresh salt. Only the freshest salt for my popcorn. Now, I'm just going to let this play for a second. I actually was at a gas supplier recently. There's his sodium, okay? Sodium, the metal that'll explode in water. And I was at a gas supplier. There's this chlorine gas. So I'm like, how do you get chlorine gas? I would love to do this demo for my classes. So I asked this gas supplier where I was buying liquid nitrogen, like it's like a welding store. I'm like, hey, could you get like some chlorine gas? And the guy just looks straight at me and goes, we don't do chlorine gas. Like, it's deadly, man. It's dangerous stuff. So anyway, I don't know who this guy is, but his name's Theo. He's got some chlorine gas, he's got some sodium, and he's about to make some fresh salt. Here we go.
The result, he claims, will be a tasty flavoring for a net full of popcorn?
Isn't chlorine deadly poison?
Absolutely. I mean, chlorine, they used it as a poison gas in World War I.
It'll be perfectly safe when these two deadly ingredients combine.
I didn't say that. I said that after they're combined, the result is perfectly safe. The actual process of combining them is fraught with difficulties.
Okay, and that's why we're dressed up like miners here.
First, a hunk of sodium in a dry metal bowl. Then, a jet of pure chlorine. Surprisingly, no explosion. Somehow, when these two bad boys of the periodic table come together, they calm down.
That white smoke
At the
is
atomic level,
salt.
sodium, an alkali metal, had an electron it didn't want, and chlorine, a halogen, wants desperately to grab an electron. Once the handoff was complete, both atoms wound up with full shells, making them stable, and able to join together to form a crystal compound we can't live without. Sodium chloride, table salt.
Now, I don't exactly see, like, a pile of salt anywhere.
Now, the salt, most of it went up in the smoke. It went in the popcorn.
Tastes like salt. The good stuff. Fresh.
Fresh
Only the
salt.
freshest salt at Tato's farm.
Crazy. I mean, they literally eat that stuff right after the chlorine gas is right there. Chemistry is crazy. So this guy, totally safe. This guy, totally safe. This guy will blow your face off before he loses that electron. And this guy will tear your lungs apart and fill them with acid before he picks up that electron. Okay, let's go down here to salt. A soft metal that reacts violently with water, sodium. Okay, an ion used in the body to send nerve signals, sodium, the ion with a positive charge. A deadly gas used in World War I to kill people, chlorine. Okay, an ion used in the body to help nerves stay calm and not send signals too easily, chlorine, the negative ion. So that's another interesting fact about chlorine is it's in your body and it's actually a calming ion. So it helps your nerves not overreact. And so you get a lot of signals to your nerves and sometimes their reaction is to say, nope, we're not sending that one off. If you have like seizures or migraines, I actually get migraines, It can be that your nerves are overreacting to stimuli. All right, a couple more notes. A bond where atoms are held together by opposite charges is called an ionic bond. Okay, and what do opposite charges do? This is what positive and negative charges do to each other. They attract. Okay, number 7 says this is what happens to electrons in an ionic bond. Well, this electron, we say it's stolen because it's completely removed from sodium and it goes completely to chlorine. So number 7, what happens to electrons in an ionic bond? They are stolen. All right, whew, ionic bonds. That's a complicated idea to be able to wrap your brain around, okay? Like the fact that atoms would lose an electron, become an ion, be attracted to another atom. That's fairly complicated. Next concept, covalent bonds, simpler.
Praise the Lord and thank you, Jesus.
Here we go. So we actually saw this clip from this video 2 lessons ago.
Here we see a single hydrogen atom traveling through the cosmos. It's made of one positively charged proton in its nucleus and one negatively charged electron. If our lone hydrogen atom happens to pass close enough to another lone hydrogen atom, their electrons, which are attracted like magnets to protons, can pull the atoms toward each other until they collide and stick together. The 2 atoms now share each other's electrons in what is called a covalent chemical bond.
Oh, did you know you had that word flash through your mind? So that was it in a nutshell, right there. 2 atoms come together and just stick together and share electrons. Let's draw it. So there are no charges involved in covalent bonds, so I'm not going to draw charges here, but I am going to still draw the electrons as red. So here's a hydrogen atom. It has 1 proton, and so it has 1 electron. Here's the other one. It has 1 proton, so it has 1 electron. And they both want 2 electrons to fill their shell. So they're going to come down here. And in the words of Finding Nemo, it's a butt.
He said it was called a butt.
Now, instead of somebody stealing somebody else's electron, the electrons are shared between both atoms. So now they both feel like they have 2. And the way this works is this electron goes around this one, and then that same electron goes around this one, and then this electron goes around this one, and then he goes around this one, and both electrons are swirling around both atoms every millionth of a second, and they start to form a big electron cloud around each hydrogen. And in the words of Finding Nemo, that's a big butt.
Wow, that's a pretty big butt.
Now, whenever I teach covalent bonds and what it is that holds the molecules together, I always show my students this, probably mostly just because I love Star Wars. This is probably the best lightsaber fight scene in all of Star Wars. Okay, this is Qui-Gon Jinn fighting Darth Maul. These should be names you know. If you don't know Star Wars, it's okay. We can still be friends. Okay, but in this moment, these force fields separate Qui-Gon Jinn and Darth Maul. And Obi-Wan Kenobi is way behind. He got knocked off. Okay, and then Darth Maul taps the force field. And that's my childhood right there, by the way. Okay, all you whippersnappers who grew up on the latest Star Wars movies and what's that stuff called? I don't even watch it. Avengers.
Dude, have some culture.
Is that even entertainment? Star Wars, my friends. Star Wars. That's entertainment. But anyway, when Darth Maul taps the force field, that's a force field, guys. Force field. My kids used to have lightsabers. Okay, when I went and asked my kids, hey, do we have any lightsabers still? My youngest son is in 8th grade now. My oldest son is in college now. They're like, no, Dad, we don't have lightsabers anymore. A little piece of my heart broke. You can't be a true science nerd and not love lightsabers. You have to say it like this. It means you love science and you love lightsabers. It's an electromagnetic force field. And in the same way, when electrons are circling atoms, like with that hydrogen atom, it's circling both nucleuses of the hydrogens. It's creating an electromagnetic force field, just like a lightsaber. And it creates this cloud of electromagnetic energy that holds the atom's nucleuses together. That's a really strong force field. It keeps Darth Maul and Qui-Gon Jinn from being able to fight each other. Okay? It's a really strong field of electromagnetic energy that is holding the nucleuses together. That's a really strong bond. A moment of science and Star Wars for you.
And you too, Chewbacca.
A bond where atoms are held together by shared electron force field is called a covalent bond. This is a strong bond, okay? In a covalent bond, the electrons are shared. They're shared and they create a force field together. So covalent bonds are strong bonds, okay? Ionic bonds are weak bonds. They're only held together by the fact that one of them is positive and one of them is negative, okay? This is weak sauce. You throw sodium and chlorine in water, you throw salt in water, comes apart, okay? But a covalent bond, you throw that in water, it stays together. So I have a metaphor in the notes for the strength of bonds. You can think of covalent bonds as bonds that are like sewn together. Like you sew two fabrics together, like those fabrics don't come apart. If you sew a patch onto clothing, like the fabrics they're connected. Versus Velcro. If you have Velcro on your shoes, it's like, it just comes off. It's easy. Covalent bonds are like sewing two fabrics together, whereas ionic bonds are like Velcro. Okay? And this really finishes off the lesson for us because my big question says, how could chemical bonds be used as a metaphor to compare God's design of marriage with the human invention of dating? Okay, so God in the book of Genesis creates marriage. And he says, a man shall leave his father and his mother and be joined to his wife, and the two shall become one flesh. Like this very strong bond will form between them. And God's heart is never that people would get divorced. Like God hates divorce. He wants people to devote themselves to marriage and be committed till death do us part. That's God's design for marriage, right? But then this culture that we live in America is this dating culture of like, just try things out, do what you want. And it's this weak form of bonding where you just, we'll try it for a while. If it's not what I like, I'll just find something new. And it's just this very weak and pathetic little commitment. And I even think, this is weird because I actually married the girl I dated in high school. I wasn't even a Christian really in high school, but the girl that I dated in high school, whatever that was, ended up being the girl who I married. We stayed together for a long time. And but this whole concept of dating is not in the Bible. The Bible doesn't even have the word dating in it. There was this other thing in the Bible, it's called courtship, that a man should really, ask a girl's dad, hey, I'd like to court your daughter for the purpose of marriage, and then it would be a quick engagement, and then you would both be committed to marriage. So anyway, you should talk to your parents about that. Those are some of my crazy ideas. It's interesting that we don't see this idea of dating in the Bible. It's really a relatively new human invention. How exactly a man and a woman should become married is a fascinating question that has different cultural approaches throughout history. God is definitely in favor of marriage and that it should last forever. Till death do us part. So, ionic bonds, weak. Covalent bonds, strong. Ionic bonds, dating. Covalent bonds, marriage. Hope this lesson helped you develop an understanding of bonding. Have a great day. Bye.